Hello everybody, welcome to Physics 2212 Experiment 3 Circuits. The purpose of this lab is to predict and measure conventional circuits and potential differences in circuits containing resistors and capacitors. Some fundamental principles necessary for this lab are the steady state assumption, which is that current flows at a constant rate when there is a non-zero E net inside the wires. Secondly, we need Kirchhoff's law of energy conservation, which includes the loop rule, or the sum of all potential differences around a loop is equal to zero, and the node rule. For a circuit in steady state, the current entering a node must equal the current exiting the node due to the conservation of electric charge. We will also be using Ohm's law and capacitance in order to conduct some calculations in this lab. The main assumption for this lab is that we will assume that resistance of wires and ammeters are negligible. Also, that the system is the circuit and the surroundings are the universe. The main results of this experiment include resistant values in a series circuit that adhere to Ohm's law, consistent values for the charging and discharging of capacitors under various conditions, and nearly equivalent RC values for time-dependent voltage across a discharging capacitor. We will first consider a simple circuit series with 2 batteries, 2 resistors, and 2 ammeters, as shown in the diagram. We predict the currents for I1 and I2 to be 0.02 amps, and the measured value is consistent with this. When one ammeter is placed in reverse, the reading becomes negative. When one of the ammeters is replaced with a voltmeter, the circuit is now open and the current can no longer flow through. Thus, the new reading of the ammeter is 0. The voltmeter, however, reads the potential difference between the gaps, which is equal to 0 minus 3 volts. Next, the potential difference in current is taken by the voltmeter at various points in the circuit as shown. When you attach the voltmeter, you alter the circuit, but the ammeter reading doesn't change because the ammeters are a low resistance instrument and the same current flows through it wherever it is connected. The results show that Kirchhoff's loop rule is followed as the sum of all the potential differences are 0. An approximate graph of potential relative to the negative end of the battery versus position around the circuit is drawn to visualize the changes of potential throughout the circuit. Using Ohm's law to calculate the resistance of each resistor, we can see that each value is true to the predicted value. Now the voltmeter is replaced with an ammeter in parallel with a 100 ohm resistor. The current going into the parallel portion of the circuit must be split between the resistor and the ammeter due to the node rule. Since the resistance of the ammeter is 0, the overall resistance decreases, resulting in an increase in current. Next, we will investigate RC circuits to observe how a capacitor charges. Over time, the light produced by the 10 ohm bulb dims as the capacitor charges. The current also decreases. The light brightens, then dims as the capacitor discharges after removing the battery. The current decreases as well. For a 10 ohm bulb, the charging time and discharging time are both around 8 seconds. For a 20 ohm bulb, the charging and discharging times are around 14 seconds for a capacitor. Next, we set up a circuit in the CCK with a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm light bulb. We measure the voltage across the capacitor with the voltmeter. We set the capacitor discharging and plot 20 seconds worth of voltage versus time data on a natural log of potential difference versus potential difference not versus time plot. Using the plot to calculate RC through the derived energy conservation equation, as seen, the predicted value of RC agrees with the measured value. If we were doing this experiment in real life and using an actual ammeter instead of an ideal simulated ammeter, we would see that a real ammeter does not have negligible resistance. So, if the experiment were done in real life, the overall resistance of the circuit would increase and the currents measured would decrease. If we were doing this experiment in real life and used a real battery to charge a real capacitor with no resistance in the circuit, then the ideal model and the real-life model would be largely the same, as the current would not be hindered within the real capacitor. However, this prediction is not realistic, and circuits may contain even minute resistance through wires, which will ultimately influence the time required to charge the capacitor. The sources of error in this lab are limited since the experiment relied upon a circuit model for data, though some human error may have arisen from recording data improperly. In general, the predicted values and the experimental values were the same, thus supporting the underlying physical principles of the steady state, Kirchhoff's law, Ohm's law, and the law of capacitance.